Okay, so we have rewritten our 3lookups function to use this bind-like operator that we had been deriving essentially from the recurring pattern in the original 3lookups function. And we have been discovering that the type of this bind operator that we have been defining here is indeed almost the same as the type of the bind operator that we have been encountering in the context of I/O, only that in the I/O context we have been using bind to sequence I/O operations, and in the context of maybe we have been using this sort of bind to sequence potentially failing computations of maybe type. Now, given that there is this similarity, we can recall that there was another function that played a role in the context of I/O, and that function was return. Return was used to embed a computation of type A into the world of side-effecting operations, I/O actions, by essentially opting out of the possibility of doing I/O, right? So I/O actions are plans for performing side effects with the outside world and ultimately coming up with a result of type A. But if we use return, then we don't actually use the option to perform any side effects. We just deliver the result immediately. And we can ask ourselves that now that we've discovered a counterpart to bind in the world of maybe computations, perhaps there is a counterpart for return as well. And that would then have to have the type return maybe, let's call it return maybe, from A to maybe A. And if we take this notion that bind is sequencing and return is embedding, where we do not make use of the option that is given to us by the type, right, which in the context of I/O was side effects, but in the context of maybe is failure, then here we would have something that lifts a value of type A into the world of potentially failing computations without ever making use of the option of failing. And that is simply just. Right? If we have anything of type A, we can turn it into a maybe A by applying just to it. And it indeed has the effect that we have something that never fails, that never makes use of the option of failing. And if we use this particular definition, we can rewrite this 3lookups function once more by calling return maybe. Now this doesn't make a huge difference, right? The big win was in the discovery of the bind function. But remember, again going back to I/O, that we had quite a number of functions that were just implemented in terms of return and bind in the context of I/O. Functions such as fmap, functions such as lift_a_2, but also ultimately functions such as filterM or sequence. And now if we have another data type, in this case maybe, that supports the same fundamental building blocks, in principle, all these operations that we have been defining in the context of I/O on top of these two operations, right, we did not make use of any other I/O specific feature except we made use of return and bind in these definitions. We should in principle be able to define them for maybe as well. So perhaps it does make sense to give a name to this interface, right? If there are multiple types, not just IO, but also type like maybe that support this basic interface, a function like bind and a function like return. Perhaps if we can abstract over that interface, give it a name, we can then define all these other functions in terms of that interface in a general way, and then we just have them available in the context of maybe as well. And this is exactly what the monad class is about. So if we take a look at the monad type class, we see that there are a couple of things that we still need to discuss, that it actually has a superclass constraint that is called applicative, that we have not yet been discussing, and that it has bind and return at the types that we would now expect as methods, right? So bind is m of a to m of b to m of b. So if we replace m here with IO, we get back the type of our original bind for the IO. If we replace m with maybe, we get exactly the type of the bind function on maybes that we just discovered. And for return, it's similarly, we have a to m of a. So if we instantiate m to IO, we get the return type on IO that we have originally been discussing, but if we instantiate m to maybe instead, we get this one. We see that there is a third method in the monad class that is the type of the basic sequencing operator, but we have already seen yesterday that this can be trivially written itself in terms of just bind, simply an invocation of bind that ignores its argument here, right? It always uses the same second action independently of the result of the first action. Right? So that is something that you don't have to really specify. That doesn't really add anything. What's more surprising here is that the minimal definition for the monad class actually allows you to omit a return as well. But that has to do something with the applicative class that already defines similar functionality. For the time being, we can just assume that monad is an interface that gives us bind and return, and in particular also basic sequencing. And bind and return on maybe are defined just like we have shown a moment ago. Right? And we can see that indeed there is an instance of the monad class for maybe defined with the definitions matching the ones that we have just shown. And there also is, unsurprisingly now, an instance of the monad class for the IO type. Right? So that's why I said before that the functions on IO that we have been using, actually many of them have more general types than the ones that we have been using them at. So that means we can now actually replace the bind operator that we've just defined with the actual bind operator, and we can replace the return function we have just defined on maybe with the actual return function, and things still work because there is the monad instance for the maybe type in the base libraries, and the definition of bind on maybe and the definition of return on maybe is just like we discussed. So for example, if I explicitly say return 3 and say I want to see this as a maybe int, I do get just 3. So the behavior of return on maybe is exactly the same as the just constructor. And similarly, this is exactly the same behavior as the behavior of bind. So that makes things a little bit simpler. We can convince ourselves that this version of 3 lookups is still working as expected. So if we call it on 3, we get nothing. right? Because 3 maps to 6, 6 maps to 12, but we don't have 12 in our list. But if we call it on 4, we do get 33. If we call it on 5, we get 41. If we call it on 6, we get nothing again. So it still works, right? But now without these two definitions in the file even. And it goes further than that, right? Remember that we said that there is do notation, right? If we have a computation written in this style, it looks a little bit like an imperative program where we are associating the result of an operation with the operation. And in the context of I/O, we said it's nicer to be able to rewrite sequences of binds with do blocks. And in fact, do blocks generalize to anything that is a monad instance. So every type that supports the monad interface, every type that essentially has a bind operator and a return operator, we can use do notation for sequences like this. So basically we can yet again go and rewrite our 3 lookups function by saying I1 left arrow rather than this invocation of bind here, and here I2 left arrow rather than this invocation of bind. And then we can do I3 left arrow and then this invocation of bind. And the return here in the end remains the same. And this still type checks, and it also still works. And as I just said, there are all these other operators that are now available to us as well. So remember sequence. Sequence, in its general form, right, is actually generalized in 2 directions. We encounter a class that we haven't seen before that is called traversable. But for the time being, we can again assume that traversable is essentially just a generalization here of lists, right? So let's just assume that we are talking about lists. But here we have a monad class constraint. So if we have the type that we have been using sequence at before, was as a function that takes a list of IOAs into a single IO action that delivers a list of A's, we can now also use sequence to take a list of maybe operations into a maybe of a list. And we have to convince ourselves what the idea of sequencing was. The idea of sequencing was essentially that it takes the original list, and between any 2 list operators, there is an occurrence of bind being inserted, right? And then all the results of all the individual actions are picked up in order, and then the resulting final list is built out of them. Okay, so in the context of I/O, that means that if we have a list of I/O actions, all these I/O actions are sequenced together, we get a single I/O action that delivers a list. Now we have a list of potentially failing computations, and this one is sequenced into a single potentially failing computation. And the semantics of sequencing is now the semantics of the bind operator for maybe, which essentially says that if any computation in between fails, then the whole thing fails. So what does that mean in the context of sequence? It means that if we have a list of maybes, right, and they're all just occurrences, right? If they're all successful, so to speak, then the overall computation, right, the combined computation, is also successful and has as its result a list containing the individual results 3, 4, 7, 10. If there is just a single computation along the way, that is unsuccessful, then that's enough to make everything fail, right? That's not the only useful function we can write, right? Of course, we could also want a function that basically picks up all the successful results and ignores the failing results. So it's a different function. Here, the behavior of the sequence function is, as before, essentially saying if any contributing computation fails, then the whole thing fails. Right? We also had this mapM operation, right? That was essentially the thing that was defined in terms of sequence and map, right? We used that to ask many questions in the context of I/O. So if we have an operation that produces an M of B, but now, before that was an I/O of B, but now that is an operation that maps an A to a maybe of B, right? Then we can take a list of A's, again, traversable we just see as list. We can take a list of A's to a maybe of a list of B's. Right? So we can use this in the context of lookup, right? Because lookup is delivering a maybe. So we can say we take in an argument, right, and we perform a lookup of that argument in our example table. Right, so that is a function that takes an int to a maybe int, so it matches the requirement of mapM, and then at this point we need a list of ints, so a list of arguments, and we get a maybe of a list of results. So we can say, let's perform lookups on 1, 2, 3, 4, for example. Okay. So if we run this, we get just of 2, 4, 6, 8, because our table is always doubling, and 1 and 2 and 3 and 4 are all contained, and because they're all contained, all the constituent operations are successful, so we get a just result. If there is just one element in this original list again, which yields to an unsuccessful operation, then the whole thing fails. Right? Again, so this is this failure propagation thing. Everything must be successful. If there is anything in there that is unsuccessful, then the whole thing fails. I'm going to leave it at this for now. Of course, there are more functions we've been discussing. filterM, for example. filterM also works in the context of the maybe type, and there are more such functions that are defined in the context of maybe. But I'm going to stop at this point for the time being and leave further discussion to the next video.